Good morning to distinguished speaker, faculties and all the participants. This is Swati Gaur from Department of Electronics and Communication Engineering, MNIT Jaipur. We have Dr. Hari Shankar Singh sir as distinguished speaker. Sir is currently working in Department of Electronics and Communication Engineering in Thapar Institute of Engineering and Technology, Patiala, Punjab. Sir has completed PhD from IIT Varanasi, formerly BHU, and has published more than 60 research papers in reputed journal conferences and also written many various book chapters and books. Dr. Harishankar sir, with more than 10 years of teaching experience, has vast research experience in microwave antennas for wireless and biomedical application. Area of interest includes microstrip antenna, MIMO antenna, ultra-wideband antennas, metamaterial absorbers, RFID antennas, and many more like this. Sir, we are honored and we welcome you for this FDP, and I request you to kindly take over the session and enlighten our participants. Thank you.
Okay, thank you, ma'am. Am I audible
Thank
to
you.
all?
Yes, sir, you are audible.
Okay, perfectly. So thank you for a nice introduction, ma'am. Now I am moving to the lecture part. So myself, Harishankar Singh. Currently, I am working as an associate professor in the Department of Electronics and Communication Engineering at Thapar Institute of Engineering and Technology, Patiala and Punjab. So today's lecture about the MIMO antenna. I will go through the theory and its challenges and application point of view. Right. So these are the different topics that I will cover in this lecture, like historical review slightly about the antenna and MIMO, then how the mobile phone evolved with the time and how it for the different generation, what the concept is being utilized, and the multiple antenna performance evaluation in the wireless communication scenario, and what are the challenges for the MIMO antenna we are facing during the design and implementation inside the mobile phone and wireless application. So one very important aspect will be isolation technique because MIMO share the common ground plane. So isolation is the very critical parameters we have to avoid, right? So we have to improve the isolation between multiple antenna elements with the different techniques. So what are the different techniques that I will discuss? And robust in the user proximity. Basically, particularly in the case of mobile phone, we use the mobile MIMO antenna in the mobile phone. So what are the interaction with the user and what are the effect of the on the antenna performance of the user body is happening? What parameter we are considering to look into? So how to tune that parameter we will discuss. And later on in the last we will discuss about the different applications of the MIMO antenna because MIMO antenna have the lots of application in the wireless application, not only limited to the mobile phone. In the wireless scenario, we are using multiple places, right? So you know how to generation of the electromagnetic wave is coming to the picture. Might be you all know, everybody know. So the it comes from the Maxwell equation. So Maxwell basically predicts the rate of change of one field will induce the another, right? Similarly, if you can see in this equation, which is the Faraday law, actually the rate of change of this magnetic field will induce this electric field. So what is the nature of this electric field? It will depend on changing the magnetic field. So in this particular Faraday equation, its nature of the induced electric field is called in the nature, which is actually circular in the nature, which is forming the closed loop because this magnetic field form the closed loop. So around that, this electric field induced will also be form the closed loop. So it will have the nature of the coil, right? So coming with the slightly historical part of the electromagnetic wave. So kite experiment might be, you know, the electrical current charge is introduced at this point of time. With the time, Michael Faraday he done the experiment of magnetic field induction, and then proved by the set of four Maxwell equation in 1864. Hertz experimentally verified the Maxwell equation in 1887. Marconi further transmit that electromagnetic wave over the large distance in 1895, and this array of antenna is introduced in the early 90s, right? So he takes the patent on this particular topic as array of receiving antenna at the base station. right? So here the MIMO antenna concept are introduced in the early 1990s. It was done by the R. L. Swamy Paulraz and Thomas Keller, right? So from 90 in 2000, after 2000, so lots of research and development has been deployed over the MIMO technology. After the introduction of this array is being utilized at the receiving antenna at the base station, right? So coming to this utilization of MIMO antenna in the mobile phone scenario, initially if you see this kind of telephone we were using. So what is happening here? The mobile, if you see in this case of first telephone scenario, the long tower and long antenna system are being utilized, right? Were utilized. But with the time, what is happening? The size and the shape and the antenna size is going to be reduced drastically. So antenna become internal with the time, and its size is also going to reduce, its slimness, everything. Even we are improving the performance, and reduction in the size is happening. So with this, lots of challenges is also facing, because in terms of size, we cannot manage with the efficiency gain and its overall performance. But with the certain techniques, we improve, not only just reduce the size, also we improve the performance of the antenna in terms of antenna performance, right? So with the time evolution, you can see early 90s when MIMO antenna take place. So with up to 2000, a single antenna element were using for the communication purposes. After 2000, most of the mobile phone where 3G and 4G, 5G evolution happened. So multiple antenna techniques are incorporated. So earlier the antenna, you can see the protruded or outside place, that is the actually called as external antenna. You can see here in the 1994 1996 mobile, the antenna placed outside this mobile phone, right? But after 2000, you can see the what is happening, mobile become antenna become internal structure. It is going to printed with over the printed circuit board, PCB itself. So as the evolution of microstrip antenna is happening, as the evolution of technology is happening, as the evolution of MIMO technology is happening, so antenna become more structure, more flexible, and even multi-band, wideband, very good performance we are also getting. So slimness of mobile phone size reduction is also happening. In the today's, you can see the lots of mobile phone is coming in the generation with the very small in size and with the very good performance. Because with the next generation 5G, even we are moving into the 6G, where the performance is very high in terms of speed, quality, and latency, right? So all of the evolution is happening because of the this technology. Not only MIMO, the massive MIMO is also coming, and other technology with the antenna performance improvement. Other technology is also coming to improve the antenna performance, right? So what are the feature of the external antenna, which was utilized earlier, which was the single dual band operation, and basically the purpose was to voice and SMS services, right? And protruding the handset, because antenna were placed outside the mobile phone. This is like the monopole antenna, helical antenna, sleeve antenna we placed over the mobile phone, which is very large in size and making the large in geometry. And it's mechanical, not mechanical robust, because design constant are there over the mobile antenna size. So that's why this kind of mobile phone are looking in the earlier days before the 90s, right? But with the time, what is happening? Antenna become internal, so it has the lots of we improve the multi-band operation. We are moving to the video and high speed communication, and integrated with the PCB platform also itself. This is the very important, because it provides a lots of flexibility for the antenna designer to design the antenna which can easily integrate over the PCB. We can easily design over the PCB, but the performance should have the what we desire, right? And mechanically robust, because we can print on of any shape, any size over the antenna. But whatever frequency we desire, we have to make sure that whether we are getting that particular frequency or not. Whatever radiation performance we require, whether we are getting or not, that must be keep in the mind. So if you see the physical characteristics, so antenna should be compact with the time, because obviously we are moving in the next generation. Everything should be miniaturized. So obviously it should be compact, easy to fabricate. Obviously not. Let's say one antenna we are designing which is very compact, but it's not easy to fabricate. So we have to deal with that also, right? So easy to integrate with mobile phone, mechanically robust and flexible. These are the very important characteristics from the physical perspective. Otherwise, what will happen? We are going to make the one parameter is very smooth, but at the cost of other, which is not actually desirable. So along with the compactness, easy to fabricate, performance is equally important, right? So from the technical characteristics, if you are looking, it should be multifunctional and multi-band, omnidirectional, less SAR production. This is the very important, because SAR is actually specific absorption rate. So it tells about the how much electromagnetic energy is going to absorb by the user proximity during the using of the mobile phone, right? So such antenna or such mobile phone we cannot use for the longer duration if producing the very high SAR. So it should be very less, and even we have the certain standard, US standard and European standard. Our mobile phone, our device should meet that standard, and less interfering with the other mobile circuitry, because its performance or placing of the antenna is very important where we are going to place. If you are placing very near to the other electronic circuitry, so obviously it will interfere with that electronic circuitry like battery, buttons, LCD, and other electronic components. So we have to design in such a way that it should have the less interference, right? So these are the technical characteristics that we have to keep in the mind during the designing of the antenna structure. So what different antenna is available we can use for the as an internal antenna which is being utilized earlier in the 90s, early 90s, where the antenna become internal. It basically utilizes slot type antenna or ceramic antenna. Initial evolution of the antenna is like that when the antenna become internal. So slot antenna is corresponding to lambda by 2. So advantage is actually it provides the very low SAR, because the large ground plane we are using on the back side of this particular slot antenna. But the advantage is disadvantage is very large size, because this antenna is designed corresponding to lambda by 2, right? And even it cannot provide the very wide band or multi-band operation. So single band operation is designed, so particular application it can handle only. Okay, but with the time when ceramic antenna came into the picture, where we utilize the very high dielectric constant material, so what is happening? The size reduction is drastically happened with the ceramic antenna structure. So advantage is it is very small and easy to surface mount, because most of the electronic PCB or any material which is being utilized in the mobile phone have the high dielectric constant. So painting of the antenna radiating structure over that material is very important, very advantageous. But the problem is utilization of very high dielectric constant cause the low gain, right, and narrow bandwidth. So this is the disadvantage. But with these advantage, disadvantage means we look into the some trade-off also. Not only this disadvantage will suppress the usability of this antenna, we cannot say like that. But if there are certain trade-off between the size and gain, so obviously we can go with that type of the antenna. With the time, we use the planar inverted F antenna, planar monopole antenna, which is very much flexible, very much robust, and also its performance is up to the mark. Okay, so this lambda by 4 PFA antenna is actually advantages like it is very small, and it provides a very low SAR, because large ground plane, again we taking the very large ground plane, we stick at the back power maximum. So that's why we can use the planar inverted F antenna. But the problem is this planar inverted F antenna is that its application within the mobile phone or within electronic devices. It's a very challenge to sustain this inverted F structure over the mobile phone. So that's why we sometimes avoid the use of this planar inverted F antenna. So later on, we move on the planar monopole antenna, which is obviously the design based on the lambda by 4, and its size is planar in the nature. But the main cause of this main problem with this is the highest. And I told you all the antenna have their own advantages as well as disadvantages. So obviously, based on our application, based on the trade-off performance, based on the disadvantage and advantage comparison, we can choose, we can select, and we can use the antenna structure. Right. So I told you up to 3G, actually we are using the single antenna for the communication. Basically, terminal was the CISO type, that is the single input and single output. In the most of the cases, we utilize the planar monopole antenna, right? But with the time when we are moving in the fourth generation, fifth generation, and 6G, even in 6G, we are moving towards the MIMO terminal, which is multiple input and multiple output, where we utilize the number of antenna at the receiving end as well as the transmitting, right? So in 5G we are using the massive MIMO. In the 6G, massive MIMO and some reflecting surfaces is also coming with the new picture. So the usability of this technology and this type of antenna structure has been increased drastically. Okay, so what is the actually why we are going to use this MIMO technology? The wireless channel suffer from co-channel interference. It provides a very limited bandwidth and power follow with the distance, right? So how we can improve this disadvantages? We can uh, ease the spectral efficiency with the multiple antenna system. We can improve we can provide the high quality of services and wide coverage. So basically, these three main important aspects of the MIMO technology, which is being utilized in the wireless communication system. Though spectral efficiency we can improve, we can provide the high quality of services and wide coverage. So basic fundamental how the channel capacity or data rate we can enhance. You can see this theorem also. So this channel capacity is given by this particular equation. As you can see here, the schematic of the number of antenna element, number of technology. So this is the CISO, this is the CMO, this is the MISO, and this is the MISO. So S stand for single, M stand for multiple, right? So this is the single input, single output. This is the single output, multiple output. This is the multiple input, single output. This is the multiple input and multiple output. In this case, we use the number of antenna at transmitter as well as at the receiver. So what is happening by using this antenna, this semantic structure in the communication scenario? You can see the capacity is drastically increased with the signal to noise ratio. Okay, so basically the main phenomena is what is happening here. We mitigate the multipath fading effect in the MIMO scenario. So base signal to noise ratio branch we select and the combine and then receive that particular information. So the overall quality, performance, data rate, latency, both we increase by using this MIMO technology, right? So the comparison of data rate is given here for the CISO and 2 cross 2 MIMO, 4 cross 4 MIMO, 8 cross 8 MIMO. So as the number of channel we increase at the transmitter as well as receiver end, so its data rate is increasing with respect to that, right? So when we are going to use this multiple antenna system in which wireless scenario, so what performance parameter is we are looking for, right? So in the MIMO system, I told you we share the common ground plane, so isolation is one of the channels. So we have to look into that. And envelope correlation coefficient, ECC is envelope correlation coefficient. When we are using the multiple antenna system at the receiver end, so obviously there will be correlation between the antenna reception. Okay. So what degree of similarity in the amplitude variation of signal received by MIMO antenna element, which is given by the envelope correlation coefficient, right? In the mean effective gain, it actually quantify the average received signal strength of the each antenna element. Say, because how much signal we are transmitting from the transmitter end, it is going to fade into the channel. So free space channel, lots of obstruction is there, reflection is happening. So due to that, the signal faded a lots in the channel. So whatever signal we have received, how much average received power at each antenna element, we must look into that. So that can be quantified by using the mean effective gain of the MIMO antenna system, right? So diversity gain is actually insight to effect of the diversity channel over the wireless link. So over the by utilizing the multiple antenna system or diversity technique, how much combined signal to noise ratio we are going to improve. Okay. So another parameter like torque and CCL, which is also crucial in the case of multiple antenna system. Torque is actually total active reflection coefficient, and CCL is channel capacity loss. So these all the parameters we also be looking for to improve the antenna performance. Also, we have to meet the certain threshold of torque and CCL, DG and MEG. All the parameters, there are certain threshold for the proper communication of the wireless channel in the MIMO scenario. Okay, so I told you in the multipath environment what is happening. Reflection will happen, refraction will happen, diffraction, interference of the signal will happen. So the effect will be what? With the time, the signal received at the receiver end is the very random. Sometimes it is going to decrease, sometimes it is going to increase. So fluctuation of signal is very, very high when we receive the signal into the multipath propagation environment. Okay, so signal is going to sometimes destructively interference, constructively interference. So it's a very random in the nature. Like, so in that random nature, how to improve the overall communication scenario or performance of the system, that's why we use the multiple antenna system. So improve the fading, improve the overall system performance, we use the multiple antenna system. So there are lots of diversity, MIMO and diversity. There are two mode of the array antenna system. Like, so diversity can be utilized when signal to noise ratio is low, and MIMO scheme can be utilized when signal to noise ratio is high in the faded channel. Right. So there are diversity, lots of diversity techniques are there, like space diversity, frequency diversity, time diversity, polarization diversity, and pattern diversity. All the diversity technique basically we use to meet the fading in the wireless channel. In the space diversity, we utilize the number of antenna signal is coming in the space from the different direction to receive in such a way that at the different time. In the frequency diversity, we use the different frequency to transmit the information over the channel. In the time diversity, we select the different time, and polarization means we utilize the different polarization aspect of the antenna structure, right? Let's say one antenna is placing which is horizontally polarized, another is the placing on the vertically polarized. So the polarization mismatch, polarization diversity will have the both the polarization scheme in the same antenna system, same over the same PCB by the utilizing the multiple antenna system, right? So by which we can improve the signal to noise ratio of the channel. Pattern diversity is also being utilized in the communication scenario to improve the overall performance. And then diversity performance we are looking, if these are the diversity techniques is being utilized in the communication scenario, so what are the important parameters? I told you, like MEG. MEG is the mean effective gain. Mean effective gain is the ratio of what? Mean received power of the antenna to the total mean incident power over there, right? So here you can see this is the transmitting antenna structure, this is the receiving antenna structure, this is the multipath propagation environment. Okay, so faded signal is coming at the transmitter end. So what is the mean received power at each antenna channel? Let's say multiple antenna we are utilizing at the receiver end. So what is the mean received power is received at the multiple antenna signal? That gives actually about the mean effective gain, and a total mean incident angle is here. So its formulation is actually given here in this equation. So in this equation, you can see one parameter is XTR, G theta, G phi, P theta, and P phi. G theta and G phi is the actually gain pattern in the theta and phi direction, and P theta, P phi is the power pattern in the theta and phi direction. Okay. So this one assumption is there. We are assuming here to calculate this mean effective gain. we assume that the uniform in the azimuth plane. Like whatever user are there, that is there are no variation in the azimuth plane and non-uniform distribution of the power in the elevation direction. So in that assumption, we can calculate the P theta, P phi, G theta, G phi, as it's a very complex to calculate the mean effective gain. If both variation of the user in both uniform azimuthal and elevation. So this is the power pattern calculation, formulation of the power pattern calculation. So we assume as a Gaussian distribution of this power in the elevation direction. Okay, so how it is vary here, you can see it's a mean at MB and deviation is 2 sigma b, and this mean and standard deviation is changing with the different scenario, right? When elevation direction is going to change and power is going to change in the elevation plane, so what we have to assume in the different scenario, like indoor scenario, outdoor scenario, and isotropic scenario, we it is given here from the different perspective. Like XPR is the cross polarization ratio. Cross polarization ratio means if it is going to horizontally polarized or vertically polarized antenna, so what is the ratio of that particularly polarization ratio we have to assume. Okay. So in this way, by using this particular equation, you can calculate this power, and by utilizing this power formula in this mean effective gain, you can calculate the total mean effective gain in the multiple scenario for the MIMO antenna, right? So another parameter is the envelope correlation coefficient, which is called as ECC. ECC is actually when we utilize the multiple antenna system in the receiver end. So signal received at the multiple antenna structure, they are going to correlate to each other. So what is the correlation of this factor is given by correlation coefficient. So it can be calculated by using two way. One is the S parameter approach, another is the far field data approach. But you know, in the S parameter approach, there are certain assumptions are there. What are the assumptions? Assumptions are like antenna should be lossless structure. Ideally, it should not be happen. It should not be there because all the antenna structure is designed over the lossy material, lossy substrate or copper. Right? One antenna is excited while other is the terminated. In this calculation, S parameter calculation, we again assume that only one antenna is working at a time, other is the match terminated with the 50 ohm. And antenna system is uniform in the scattering into environment. This can be done in the second way, but ideally both the antenna is simultaneously working in the MIMO environment. Okay, so antenna is in uniform scattering environment. This is again not going to happen in the real scenario. So this is based on this assumption, calculation of S parameter is very tentative, not the very close value, not the very accurate value. Okay, so that's why we are less likely to go the calculation of envelope correlation coefficient with S parameter approach. We go with the far field data approach. So in this approach, we actually consider the variation of power pattern and field pattern in the free space environment. Okay, so XPR is the vertical power to horizontal power ratio, which is actually the cross polarization ratio actually. And you can see this Aij is the coefficient which can be calculated by using the field pattern and XPR and power pattern. So this is the more accurate, this power and field variation in the free space environment or actual scenario environment is varying with the different scenario in the different environment with in indoor outdoor isotropic environment, this power pattern is vary using this mean and standard deviation. So by utilizing that power pattern and field pattern, you can calculate this envelope correlation coefficient. So this is more accurate and more realistic in the actual scenario of the wireless channel, right? So everybody should prefer to calculate the envelope correlation coefficient by utilizing this far field data rather than S parameter approach. This is the simple, but it's not accurate in the practical scenario. And its desirable value for the MIMO antenna cases would be 0.5. Okay, 50% of the correlation should be. And third important parameter if you are looking for the MIMO antenna case, that is the effective diversity, right? So effective diversity gain is actually nothing but it's the diversity gain multiplied with the efficiency of the base branch. Base branch means let's say we are using the number of antenna element which is producing the maximum signal to noise ratio at each channel. So that we consider as the efficiency of that particular branch, right? And diversity gain is what? Diversity gain is actually tells about the how much signal to noise ratio of combined antenna system with respect to single antenna system. Right? Let's say I am using the single antenna system, we are getting the some signal to noise ratio, and corresponding to that we have the probability. Okay, so the for fixed probability of error, if you are using the multiple antenna system, so what amount of signal to noise ratio is going to enhance? So that is actually give you the diversity, right? So it's the formulation is given here. This is the actually RC by sigma c divided by this signal to noise ratio of the base branch. This is in the graph is also given here. For the two element antenna system, I am representing this diversity gain. As you increase the number of antenna elements, signal to noise ratio is drastically improved for the fixed probability of it. Okay. So as we increase the number of antenna, diversity gain will increase. So MIMO performance, again, we are looking for the multiplexing efficiency. Multiplexing efficiency is actually defined as a power penalty of realistic multiple antenna system in the given capacity compared to the ideal antenna system, right? So again, it is related with the correlation coefficient. This is the efficiency of the individual antenna element multiplied by this is the envelope correlation coefficient. If you see here, right? This is the correlation coefficient. Envelope correlation coefficient is square root of. So how effectively we are going to correlate both the antenna system and working individually, and what are the efficiency in that scenario that will give you the multiplexing efficiency. Okay. So when we are using these mobile antenna structure in the user proximity, so these two parameters are also important. I will tell you later on in the robust antenna performance. This is the specific absorption rate and total radiated power. Okay. Now I'm coming to the challenges part. What are the challenges during implementation of MIMO antenna? Right. So these are the different challenges like antenna miniaturization, multi-band wideband operation, high isolation, and robustness. Because where this technology MIMO antenna system is being utilized or applied, which is very small. Any devices or gadgets that you are being used, which is very compact in nature with the time. So antenna miniaturization is very important, and miniaturization will not only come at the cost of bandwidth, but also at the cost of other performance like efficiency and gain. Again, we can do one parameter, meet the one challenges at the cost of other challenges. Like from the antenna designer view, we are not looking that we can do only this. We have to always keep in the mind that other parameter is affecting or not. Like let's say I'm going to design a miniaturized structure, but it may provide the very single band. But again, we want to design the multi-band or wideband nature, right? So we need to have the wideband structure. If you are going to miniaturize the structure over our aperture size, you are going to miniaturize. Okay, so you cannot get the very wider bandwidth. So what are the applications? What are the criteria for the application? And for what purposes we are designing the antenna must we look? What are the input for us? Then we need to design the antenna according to that. Again, let's say I am designing the multi-band wideband antenna, but its overall aperture is very high. So obviously, it can cause the user interaction, or even it will reduce the isolation between each antenna element. So we have to look into that also. So these are the challenges actually for the any devices, like we have to miniaturize. So what are the different techniques we can utilize for miniaturization, for multi-band wideband operation, for isolation, for robustness? We will discuss one by one. Okay. So first, let us see what are the techniques for antenna miniaturization we can employ for the MIMO technology. So I told you antenna miniaturization comes at the cost of band, right? So miniaturization usually comes at the price of reduced bandwidth, usually in the most of the cases, because overall footprint of the antenna is going to reduce because of miniaturization. So overall aperture size will reduce. It means bandwidth will going to decrease. Over the quality factor will also be reduced. So what are the techniques? We can use the high permittivity material. We can use quarter wave patch, planar inverted F antenna, capacitive loading, slots, and winding. These are the techniques can be utilized to reduce the antenna structure. I'm going to discuss very briefly each of these techniques, how it can work. So, the size of antenna, a simple microstrip antenna, if you are looking for, the size is calculated by simple this geometrical formula. Okay. So, where you see the size is inversely proportional to the square root of dielectric constant, right? So, if you increase the dielectric constant of the substrate over which the antenna is printed by 4 times, so what is the size of this antenna structure is going to reduce? It's going to reduce by half, because ultimately square root of this permittivity is there. Okay, so half of the antenna structure is reduced. So physical structure you can see is the just half in the length and in the width. So what this can miniaturize the structure, but what is happening here? The problem with the band. So at the cost of bandwidth is uh, this thing is coming, right? Another quarter wave patch can be utilized. Quarter wave patch is where the field, where field will be zero, we can just sort at that particular point, because it cannot affect the resonance structure, resonance at that particular frequency, but physical aperture of this antenna is going to be reduced. Main radiator is going to reduce. So let's say field is going to zero at half of this particular so we are putting here the sort circuit via which is connected to the ground plane. So overall length of this structure is going to be half of the main radiating element without going to changing its particular resonance frequency. So total electrical length traveling over this patch and ground is same as the same length of this particular radiating structure, but the physical size is reduced just half. Okay, so but again the bandwidth is lost. Okay, so planar inverted F antenna is also one of the technique in which we utilize the structure of inverted F with the nature of top plane as a planar. So this PIFA is actually introduced from the inverted F. PIFA means planar inverted F. Initially, inverted F antenna came into the picture, but inverted F antenna is what you see here. So the structure from the front, it looks like the inverted F, but the top radiating element you can see this schematic. This is the in the inverted F, it is a like a wire. Okay, so this produces the very inductive effect, not the capacitive effect. So its bandwidth is very low, though its size is very same as of inverted F. But when we increase they reduce this radiating patch from the wire to the planar structure, like this radiating structure. Okay, so it increase the capacity effect, overall capacity effect it enhance. So bandwidth is slightly increased as compared to inverted F antenna. So planar inverted F antenna is you can say it can not only reduce the size but also provide somewhat very more bandwidth as compared to inverted F antenna. Okay, in this structure, what we are using? We are using the feed line and we are using the sorting line. Okay, sorting line we are using where the field is actually zero. There are no any effect, much effect over the current path. And this feeding point is tuned to get the maximum impedance matching from this sorting points. So usually we keep lambda by 8, lambda by 8 and lambda by 4 distance from this starting point to proper impedance matching between the antenna structure and the transmission line. And further to increase the miniaturize the antenna structure with enhanced bandwidth, we use the capacity load. You can see here the additional radiating element is placed in between the substrate and this ground plane and the radiating structure. This again produce the more capacitive effect over the antenna structure. So overall quality factor of the antenna structure is going to enhance and increase the bandwidth a little bit as compared to the planar inverted F antenna. This is the again miniaturization technique like slotting of the patch, because you know slotting over the patch is actually alter the current over the patch, right? So conventional patch will have the certain current distribution over the patch as the circular or rectangular patch has. But when slot will introduce over the patch, the current is going to alter with the current path around this slot. But what is the length, what is the width, what is the size of this slot? This is the very important. Otherwise, it is not going to affect alter the electrical current and not going to help into the miniaturization. So its size is very important. In you put this shape and size in such a way that it should have the alteration in the current so that it can take the longer path of the current. By using the same physical size, you can reduce the frequency. In earlier miniaturization technique, you can see the antenna size is actually physically reduced. But in this case, what is happening, this is electrically reduced, right? Why? Why I'm saying this electrically reduced? Because physical size remains same. Let's say there are no any slot. We are feeding at this particular point. It provides the resonance at particular frequency. And after that, I am putting the slot at the certain places. So what is happening? Current over the patch is altered now. So due to the alteration of this current, what is happening? Whatever resonance is coming earlier is now shifted towards the lower frequency. Okay, because the current travels the longer path. So this is again one of the miniaturization technique. By keeping the same footprint, you can reduce your resonance frequency towards the lower side, because obviously at that particular side you have to design the larger aperture, but we are not going to increase the aperture. We are keeping the same aperture, we are increasing the electrical length of the current over the patch. Okay. Again, the next miniaturization technique is the mindered line. Like mindered line, you can use the same footprint, but you can use the number of loops over the antenna, over the radiating element, so that it can take the longer distance of the current path can go to the lower. Okay. So these are the different techniques to miniaturize the antenna structure. All these techniques can be utilized for the designing the MIMO antenna structure for the miniaturization of the antenna. Now another challenge is to getting the multiband wideband. Okay, so how to get the multiband wideband? Getting wideband is very simple, but again, getting the wideband will have the cost other parameters, right? Like efficiency and gain. You know, what is the bandwidth can be increased by simply increasing the thickness of this substrate. But you know, when we increase the thickness of this substrate, what is happening if you are feeding with the coaxial line? Inductance effect will if increase. So this inductance effect will cause the narrower the bandwidth. So this limits the bandwidth can be further trade off. So obviously during the antenna designing, you have to always the trade-off between the performance, size, shape, geometry, everything. So that's why in most of the cases, if you see the mobile phone, almost every mobile company have the different shape and size of the mobile antenna. You know why? Because the antenna engineer commented the last because every circuitry, everything plays over the mobile phone. Then manufacturer says that this is the space for you. You can design this type of the antenna. This performance is required, and you have to design. This is the space is required. Now you can design. So that's why in that particular space, lots of optimization trade-off and happening within the mobile phone to design the particular antenna for the particular application with the particular performance. Okay. So similarly here, though what is happening? We increase the bandwidth. So what is going to happen? Inductance in increasing. So L-shaped probe we are utilizing to mitigate that problem. Okay, so we compensate this inductive effect by using this L probe to introduce certain capacitive effect, so nullify that inductive effect. So overall performance will remain same, means with the enhanced bandwidth we can get, right? Even some other fitting technique is also there. Aperture coupling and proximity coupling we can use to improve the bandwidth without using this LSEM probe, right? That type of structure we can also utilize. So capacitive hot tap top hat we can use on the probe for the actually for increasing the nullifying this inductive effect. So what we are doing here, this is the pad, this is the feeding point was there. So this inductance is increasing, causing the problem to limit the bandwidth because we are increasing the substrate height. So we are creating the capacity effect between the patch and this feed point. So this capacity effect nullifies the inductive effect, overall bandwidth will increase. And by using the stacking of the substrate, we can also improve the bandwidth of the antenna. So these are the technique are being utilized in the most of the MIMO antenna, where what is happening? This is the microstrip line structure. This is the substrate. Over the substrate, we are using the ground plane. So ground plane have this slot. This is actually one of the feeding technique of the antenna, which is actually aperture coupling, right? So this antenna patch radiating structure is placed over the foam. So this coupling of this microstrip line electromagnetic field is coupled through this slot, and the bandwidth is slightly increased because effective dielectric constant of this overall substrate is increased, right? So in this way, we can also improve the bandwidth. Stacking of the patch is also there because there are number of patches there, which size is very comparable. So that produce very close resonances, and that resonances match to combine to each other, and they provide the overall larger bandwidth. Okay, so this is the aperture coupling feeding will provide. All these are the aperture coupling feeding is there, which is also provide the very improving bandwidth. But it has the also problem. Problem is what? Because microstrip line provides the very spurious radiation because it is placed on the substrate. So some fringing field is at the edges of this microstrip line is there, which is create the lossing in the nature. So micro somewhat in sometimes aperture coupling may not be suitable for the certain application, right? And some parasitic patches is also there to improve the bandwidth. Like we use the patches apart from the radiating patches. So parasitic patches is what which is depend on this main radiating. There is a mutual coupling between the main radiating element and non-connecting element, non-radiating element. You can say also. So the what is happening here? The placement of this parasitic means parasite, which is which is depend on some other radiating element, right? It's not directly fed with the microstrip line or coaxial line. It will get the power from the main radiating element, then contribute the radiation in overall radiation. Okay, so in this way, we can increase the overall bandwidth because multiple resonance will coming to the nearby, ultimately which are merged together and giving the improved band. Okay, so placement of this parasitic element can be at the non-radiating edge as well as radiating. Okay, so what the factor of bandwidth improvement you can say here by the factor of 3, 4, 5. what the factor of the bandwidth we are going to improve or increase. So according to that, we have designed our parasitic element and place the parasitic element near to the radiating element. And apart from there are in that scenario there are no any physical connection between these two radiating element and parasitic element. But we can also connect these two elements, also provides the size reduction as well as the bandwidth enhancement, right? So this is called direct couple patches, which can be not only increase the frequency, decrease the frequency, but also improve the bandwidth. Some slot technique is also there to improve the bandwidth, like double slot, single slot. It can also help to improve the bandwidth, right? So if we these are the bandwidth improvement techniques. Some of the multi-band antenna system structure are there. So multi-band antenna structure is nothing but corresponding to the frequency. You can choose the size of the radiating arm. You can connect directly with the main radiating element, or you can place near to the radiating element. You can get the multi-band operation. Like in this structure, you can see, right? So this can help to get the multi-band as well as wideband operation. So to get the wideband operation, your parasitic size should be approximately same as the major radiating element. But in the case of dual band operation, your parasitic element should be corresponding to the resonance frequency or wavelength which you desire to obtain. Okay, so this is the technique to obtain the multi-band operation in the antenna system. So all these technique you can apply in the MIMO technique, MIMO antenna element during the designing a MIMO antenna element to get the multi-band wideband operation. Okay. Now coming to the challenges with the high isolation. So why isolation is important? Because when this is the radiating element, when we fade this radiating element, what is happening? Some wave is reflected, some diffracted, and some transmitted. So whatever transmission wave is there, that is the space wave that is going to radiate in the free space, which is actually desirable. But diffracted, or you can say, which is undesirable, which is diffracted and travel laterally over the surface of the substrate. So these waves are actually called as the surface wave, which is undesirable in the nature. Why it is undesirable? In the MIMO antenna case, multiple antenna scenario, what is happening? We are placing the multiple antenna system over the common substrate. Like over the common substrate, even the ground plane is also common. So what is happening? Not only coupling of this ground plane wave, but also this surface wave over the substrate is also causing the mutual coupling to each other. So this degrade the performance of the each antenna element. This antenna element may defect the performance of this antenna. This antenna element may affect the performance of this antenna. So each antenna element mutual couple strongly to each other due to this surface wave. Okay. So how in the this multiple antenna system, how the coupling is happening? Possibility of coupling is possible. First is the space wave coupling. Second is the surface wave coupling. Third is the ground wave coupling, ground plane coupling. Because the common ground we are using in the most of the MIMO antenna cases. So we have to avoid this isolation is the very important in the case of multiple antenna technique, because antenna placed very close to each other. Let's say we are designing the lambda by 2 antenna. So obviously we have to keep the antenna element at least lambda by 2 distance to avoid this kind of surface wave coupling. But usually in the mobile or any devices which is we don't have the large space, that's why our antenna element will be very closer. So due to the closer distance, so what is happening? This surface wave coupling will happen. So it reduces the antenna performance are very highly uh, coupled antenna structure will be there. So we have to remove this mutual coupling. We have to isolate these two antenna elements and work independent. So for that we have the different techniques like defected ground structure technique. It's actually working as a filter kind of structure. Okay. So certain capacitive and inductive effect we create over the ground by using the different shape and geometry, which actually block that particular frequency, that particular isolation between the antenna element, so that the antenna cannot couple to each other. Okay, so it perturbs the field over the distribution, which is distributed over the surface, and we disturb the electromagnetic field which is traveling from one point to one antenna element to another antenna element. We reduce in the coupling in that. So lots of shape and size you can see in the literature. I will show you the later on, how this defected ground structure is going to reduce the help to reduce the mutual coupling between antenna elements. So these are the different conventional shape and size which is being utilized in the different literatures, different papers, and this is actually nothing but acting as a filter by creating the certain L and C between the antenna elements. Second is the neutralization technique. Neutralization technique is actually in which the one strip, very thin strip, which is corresponding to lambda by 20, lambda by 20, lambda by 16 thickness, which is directly connected to the main radiating element, and its distance should be in such a way that it travel with the same phase, same amplitude with opposite phase. Like if distance is chosen in such a way that we have to keep that amplitude will remain same and phase will at this point will have the out of phase. So this neutralization line will cancel out the space, radiation to each other. So ultimately we get the enhanced isolation between the antenna elements. So this works based on the field cancellation concept of the two antenna elements, which compensates the existing electromagnetic coupling, right? So it can be suspended line or it can be printed over the substrate. Like if we are using the planar inverted F antenna, so it will be suspended. If it is planar monopole antenna, it will be printed like this structure. In Su et al, you can see here, this is the neutralization line which is connected and printed over the substrate. Okay, this is the planar monopole antenna, so we can implement the neutralization line in this way. But in Diallo et al, they have used the planar inverted F antenna. So in that case, this line is suspended over the air. In that case, this is the very difficult to maintain the height or sustain over the certain height of this neutralization line. So again, it's a trade-off between the application requirement and design, right? So electromagnetic band gap structure is also utilized there. So this EBG means electromagnetic band gap. So this EBG is basically helpful to reduce the surface wave. So whatever surface wave isolation techniques, we can only not only reduce the isolation from the surface, we can also have the reduction in the ground coupling and the space coupling. Okay, let's say at a time I am removing the isolation between the surface coupling, it may couple through the ground, it may couple through the space. So we have to look into that by utilizing one technique, how much isolation we are getting. Maybe by UVG we are not getting the good isolation. At least 15 dB isolation we require between the antenna element, right? So this electromagnetic band gap structure is utilized here by Su et al, in which they have designed the EBG in such a way that that provides the band gap at that particular rough resonance frequency. So surface wave, whatever coupling between from antenna 1 to antenna 2, that is going to suppress and filter out by using this EBG structure. So antenna isolation is ultimately enhanced, right? Orientation of antenna element is another technique to improve the isolation, in which we place the antenna structure in such a way that whatever space wave coupling was happening, that can be reduced, right? So we place the antenna like orthogonal to each other or certain degree of add to each other, so that that can have the space wave coupling reduction. In that particular literatures, they have utilized the orthogonal placement of the antenna structure 1 and 2. So vertical and horizontal polarization of the antenna we are getting at port 1 and port 2. So the whatever space wave coupling was there, that is reduced. Okay. So pattern diversity can also be utilized for the isolation enhancement. In most of the cases, we design the MIMO antenna in such a way that, but the coupling is also happening. So this, if this is not helping to improve the isolation, we can go in the another way like surface wave reduction or ground wave coupling reduction. Okay. Now, if antenna is designed perfectly, if isolation is okay, then what is the problem? Then we are going to use the antenna structure in the user proximity, right? In the user proximity, what are the challenges we look into? Like the antenna interaction with the human body will degrade the performance of the antenna structure. So, what the parameters we are looking for in the user proximity? What are the criteria for that? You can see here. In the multiple antenna system, what is happening? Single antenna system, you can, SAR is what amount of energy is absorbed by the human body, right? But in the multiple antenna system and the MIMO antenna system, what is happening? SAR of antenna 1 may affect the SAR of antenna 2. I mean, field of one antenna may affect the field of another antenna, and similarly, and vice versa, right? So what is happening? Total SAR we cannot find by just simply calculating the SAR1 and SAR2. So for that case, what are the effective SAR in the multiple antenna system? Multiple antenna system SAR is actually saw to peak location spacing ratio, which is actually summation of SAR1 and SAR2 divided by distance between these two peak SAR. Okay, distance between these two peak SAR. By utilizing this formula, you can calculate the saw to peak spacing, saw to peak location spacing ratio, which will give the effective SAR of the multiple antenna system in the human proximity. And it should be less than 0.3 as per FCC, Federal Communication Commission. Okay. So we can calculate this SAR in the different scenario, like when this is the top position, typing position, handset position. There are different position of using the mobile phone or devices. You can place the antenna in that scenario and you can calculate, like, right? So most of the mobile manufacturer optimize the antenna by keeping the mobile antenna at the top or bottom or the left or the right, whatever they find the suitable position, they design the antenna. Okay. In that position, you can just simply see and optimize and see what are the effect over the performance of antenna you are placing the antenna over the this PCB places. What are the gain, what are the efficiency, what are the total radiated power, what are the SPLSR we are getting by placing that in a different scenario itself a study. Okay. Now the second important thing is in user proximity is the is actually total radiated power. So when we feed the antenna structure with the transmission line, the if proper impedance matching is there between the transmission line and antenna structure, so radiation is going to happen. But what is the problem when antenna is placed in the user proximity? The total effective power is not going to be radiated or received. Some power is going to be absorbed inside the human body. Right? So what is the total effective radiated power that we have to take into the account? That actually can be calculated by using the total radiated power. So this is the formulation of the TRP calculation, and as per CTIA, Cellular Telecommunication Industry Association, the TRP is formulated by using this PA multiplied by radiation. So what amount of power is delivered to the antenna? I mean, what power is coming to the antenna is not delivered to the antenna. Some power is going to be absorbed by the human body, right? And what are the radiation efficiency of the antenna? That will give you the total radiated power. Okay. Now coming to the performance of the antenna in the user proximity. Let's say what I am telling you, your device, let's say, used in the different cases. If talking about the mobile phone, so your mobile phone can be utilized in this case or this position, because this position is simply, you can say, data mode. When you are typing, you are seeing there your mobile. In the dual hand mode, most of the time, sometimes you are using both hands. So what are the effect? In that case, you have to look into. And prior to position this device in user proximity, what are the other components over the antenna can be placed? You can look into that. Whether with these elements, like when you are considering speaker, main PCB, LCD, component, battery, housing, buttons, etc. With these components, your antenna performance is how much? Whether its gain is going to be decreased or not, its performance is going to be decreased or not. If anything is disturbed, so you have to look into the design, you have to look into the position, you have to look into the isolation, everything. And once it is okay, its performance is okay with all the circuitry, then you have to enclose with the box. If it is again okay, then go for the simulation, or you can do check with this certain simulation, this certain setup. You can do all these things in the simulation as well as in the experiment. In the experiment, what is happening, you can create this model by using the certain shapes. These shapes are available in the market, or even you can design by using the 3D printing. So by using the certain materials, whatever material is most closest to this human body, you can measure the dielectric constant. You can shape that particular shape. And after designing the antenna, placing over the case by using multiple elements, you can test your antenna in that particular scenario. You can calculate total power, you can calculate efficiency, gain, S parameter, and all. So if every performance is okay, then you can say our antenna designing is okay. If anything problem, then you have to look into the design and optimization at any point of time. So antenna should be must be robust in user proximity, because ultimately whatever device we have developed is going to be utilized by somebody in some certain practical cases. So whether in that practical cases it is okay or not, you have to look before going to launch into the market. Okay. So what are the, now coming to the application of the MIMO antenna? There are lots of application of the MIMO antenna you can see here. For the different application, in this case, they have designed the 4-port MIMO antenna by Abdullah et al. You can see 4-port where they have designed. This is the port 1, port 2, port 3, and port 4. Actually, this is the four element antenna structure. How it is four element? There are two element in one antenna, and second element is mirror image to another. So they are actually providing the space diversity with the this kind of geometry. Okay, and they have designed the structure for the approximately 5.8 gigahertz, which is actually sub 6 gigahertz application they have targeted. So as parameter you are looking, all the four elements are providing the same reflection coefficient, right? So they utilizing the polarization diversity as well as space diversity to for this particular application of sub 6 gigahertz. Okay, how they have targeted the design criteria. This is the main radiating element, this is the feeding point. This is the main radiating element, this is feeding point. And the ground plane is protrude somewhat to reduce the mutual coupling between the antenna structure. So they are looking for the isolation between these antenna elements between port 1 to port 3, port 1 to port 4. Okay, they're not looking the isolation between port 1 to port 2, because they are directly connected to each other, which are with the direct element. And even they utilize the somewhat neutralization technique to somewhat get the isolation between port 1 and port 2 maybe. Okay, in Sarkar et al. In 2017 proposed the compact four-element SRR loaded dual band MIMO antenna for this application, like WLAN, WiMAX, Wi-Fi, 4G LTE, and 5G application. 5G not the millimeter wave. They are targeting the sub 6 gigahertz MIMO application, right? So in which what they are targeting, they have designed the main radiating element, and they have placed the SSR for the mutual coupling as well as the bandwidth enhancement. Okay. So without SSR loading, you can see the mutual coupling is around the minus 50, minus less than minus 10 dB at this particular resonance of frequency. But when they are placing this SRR, what is happening? SSR is actually acting as the electromagnetic band gap coupling, which is creating a acting as a filter at this particular frequency. So they suppress the amount of surface coupling between the antenna element to each other. So the drastic improvement of isolation is happening at this particular frequency. So the splitting resonator as a EBG structure they have been utilized here for isolation enhancement between the antenna. Another Amit Kumar et al. Proposed the high isolation compact 4-port MIMO antenna loaded with CSR. Rather than SSR, they have loaded the complementary split ring resonator for the multiband operation. This is again multiband operation, which is resonate at this 3 resonance frequency. So if you can see here, when there are no any, this is the back plane, this is the back means ground, and this is the main radiating top plate. Okay. So what is happening here? You can see the isolation is very much problem at this particular resonance at around 1.8 gigahertz, 2 gigahertz. Okay. So it is more very closely around minus 8 dB isolation is there at this particular frequency. Now what they have done, they have placed this complementary split resonator between the antenna, right? So you can see drastic improvement of the isolation is happening by placing this complementary split ring resonator. So what is the effect of this CSRR? This is actually providing the surface current reduction. What is surface current? Whatever surface current from antenna 1 to antenna 2 is going to couple, because no alteration in the ground plane is there. No alteration over the space wave is there. So only alteration is there. What alteration is only done at the top plate over the substrate. They have designed this CSRR. So isolation is approximately we are getting they are getting around minus 20 dB, which is quite satisfactory at that particular frequency. So this is acting as a simple electromagnetic band gap structure, which is create the filter kind of structure at that particular frequency. Okay. And in this particular structure, this structure actually simulated and developed by us. So in this structure, we have utilized the protruded ground, means defected ground structure, to enhance the isolation at this particular frequency. So without this ground structure, what we are getting, we are actually we were getting very less isolation, approximately minus 10, minus 8 dB. But when we enhance, when we place this, actually the main problem of the isolation is at the lower frequency. Means when we are utilizing the LT700, which is the low frequency, 4G frequency band. So in that case, we were getting less than minus 4 dB isolation at this particular frequency without this protruded or DGS. But when we use this modified ground structure, we use on the back side. So somewhat we are getting minus 12 dB isolation at this particular structure. Okay. And apart from that, some authors also develop another structure. Lots of structure have been developed by the different authors, like Zung et al. Have developed in 2005 truncated ground structure, in which they have modified the ground structure to isolate the antenna structure. Mogadasi et al. In 2014 and 9, they have slot structure between the ground plane. This is a very thin structure. You can see this is the one main radiating element. This is the another main radiating element. They are mirror image to each other. This is the top plane. This is the ground plane. Okay. Similarly, they have created the MIMO structuring of this. So they utilize triangular shape radiator. They have truncated ground, one side where the microstrip feed, on the other is electromagnetic coupled via hole. in the ground to similar but small parasitic type. Like actually they are not utilizing there are a single antenna element. They are utilizing the slot technique for the multiple antenna performance multi-band operation. And here the MIMO antenna is placed and isolation is enhanced by using this protrude ground, right? Inverted Y stub is attached to this ground plane to enhance the isolation. This is the early 2000 in 2011 they have developed this kind of structure. And with the time, author have discussed about the different isolation technique, not only from the protruded ground, but along with the protruded ground, some of the placement of the antenna structure and stub slots is being utilized for the isolation uh, enhancement between the antenna structure. So, Gogas et al. In 2013, you can see here the multiple antenna structure is there. This slots is created here for the bandwidth and performance enhancement. And at the back side of this structure, they utilize the ground structure, modified ground structure for the isolation enhancement over the wide bandwidth because they have designed this particular antenna structure from for ultra wideband operation like 3.1 to 10.6. So they achieve the ultra wideband isolation by using this structure because over the ultra wide operation isolation achievement is slightly tricky. So with this structure, certain optimization with the ground plane, they have achieved around minus 15 dB isolation over the given range of frequency. Okay. Some authors have utilized complementary, self-complementary antenna structure for the isolation and performance enhancement. Now, in this case, you can say Liu et al. Have designed this complementary structure over the ground. Like this is the main radiating element, and complementary of that has been created over the ground plate like this. And further, they have modified this structure to make the defective ground structure in such a way that provides the isolation better isolation over the given bandwidth with the reduced size. Because you know the if you compare the size with the previous antenna structure is footprint is very less as compared to previous one, right? So if footprint is low and isolation is better than minus 15 dB, so that's why we can say the satisfactory performance. In some of the antenna cases, they have utilized the stops and slot structure to get the higher isolation over the given wider frequency range. So all these are the different authors have discussed the different techniques to get the high isolation and to miniaturize the antenna structure to get the isolation and to perform the performance to enhance the performance in terms of multi-band, wideband, in terms of performance enhancement like gain, efficiency, and so on. So here the another some of the techniques like in this mentoring line is utilized and stops are utilized for the antenna size reduction and isolation enhancement, in which decoupling structure are introduced over the ground plane. And this is the unique structure you can see here because in which the shared ground plane is utilized. Shared ground plane means there are two feed points, same radiator is there. So this one feed point is here, another feed point is orthogonal to that. And the isolation is actually achieved by using the stubs on the ground plane and which is just back to the main radiating element. So this type of antenna structure not only providing the polarization diversity, but also because horizontally and vertical polarized, we are getting the radiation from these two feed points. And backside of this stub, backside stub connected to the ground plane will enhance the, will help the introduce the enhance the bandwidth along with the isolation. Because by increasing the bandwidth, there are certain coupling between the main radiator and back plane of this modified ground plane is happening. So overall bandwidth is slightly enhanced. That's why they are getting, 2.4 to 12.75. 2.4 means it is covering the Bluetooth along with ultra wideband frequency. Though interference may be happening between the Bluetooth and UWB, but with the overall gain performance, they are obtaining from 2.3 to 5.2 dBi. And efficiency is also good. Even 75% efficiency, we are getting more than 50 to 75%. And isolation is quite satisfactory, less than minus 15 dB. minus 15 dB over the wide band is critical, though they are getting by using this stops and this orthogonal polarization. So ultimately, there are two techniques are utilized here: ground modification and placement of the antenna. Okay, and in this structure, Gorai et al. Have proposed this fractal structure which is placed between the antenna element to increase the isolation between the antenna. Okay, and also they have utilized the quasi-self complementary nature of the antenna structure over the ground plane to enhance the isolation. So, combination of techniques can also be utilized for the performance enhancement. Like in the multiple antenna system, we are talking about the like we can increase the gain, we can reduce the size, we can improve the bandwidth. Whatever technique I told you in the challenges part, like multi-band, wideband operation obtaining, isolation obtaining. So all these actually design have utilized that technique in the different way. Okay, so what are the application target is there, what are the performance we are looking, so according to that you can club the techniques and design the antenna structure, right? So in this technique you can see combination of these two techniques are applied here. Protonic ground plane and electromagnetic band gap coupled up structure is utilized. Okay, and these two radiator are mirror image to each other, and slotting over the patch is introduced here to reduce the size of antenna structure, and mutual coupling is there, parasitic element is there to place the to getting the wider bandwidth, and ground modification is also there to get the wider bandwidth. Okay, and isolation, why it is very high, because the defective ground structure is being utilized by using the concept of the electromagnetic band gap structure. So they are getting more than 20 dB over the wider bandwidth is very very important. So it's a very important, very good performance in terms of isolation as well as bandwidth. Okay, so this is the another layout. You can see the orientation is the orthogonal to each other. That's why they are getting the very high isolation, less than minus 16 dB. They are obtaining over the given bandwidth, wider band. Okay. So these are the different antenna structure that I told you, and different application. For different application, they have developed the antenna structure by using combining the different techniques which I told you in the previous slides. So these are the references that I have followed for the designing the antenna structure, microstrip antenna structure. These two very important. These are the books actually. This is very very important if you are going to learn about the microstrip antenna, designing of the microstrip antenna, its formulation theory. All these books are very very important. And these are the general difference of the microstrip antenna designing. These are the CAD formulation you can find in these books also. Okay, so this is all about from my side. If you have any question, you can ask and we will discuss.
Sir, there are few questions from the participants. Can I say the questions for you, sir?
Yes, yes, sure.
What is the value of diversity gain in MIMO? It should be approaching to 10 or changing according to the number of elements. Different researchers have different point of view. What's your point of
Uh,
view, sir?
ideally, whatever what is happening, if ideal case you are taking, it's going to approach to 10. But but that is for the certain probability of error. If in the actual scenario when probability density function is changed, in the real scenario xpr is changed, it's not going to always be 10. If you are getting the 10, 10 is a very ideal scenario. In not every scenario you can get the 10, right? So according to your scenario, indoor, outdoor, isotropic environment. So most of the time in isotropic environment you will get the 10. But indoor, outdoor environment, as the XPRV you will change, mean deviation, standard deviation you will change, your diversity gain will change. And as the probability of error will increase, change means increase or decrease, your diversity gain is also going to increase or decrease, because diversity gain is actually improvement of signal to noise ratio of combined antenna system with respect to single antenna system, and the certain probability of error, right? So that's why I'm saying in the isotropic scenario where there are certain fixed probability of error, so that's why you are tending towards the day. But in ideal scenario, you are not going to get the thing.
Okay, sir. Sir, next question is how to increase the gain of antenna without increasing the dimensions or without changing the antenna design?
Yes. Uh, there are lots of technique to increase the gain of the antenna. Means how to increase the gain, first you have to understand. There are gain to increase the gain means how much maximum amount of power delivered to the antenna structure with respect to the input antenna structure, right? So what are the losses is there? You have to reduce that without antenna structure. Let's say you don't want to change your antenna structure, don't want to change your shape and size. So you have to compensate with the substrate, right? So substrate you can design in such a way that should be low loss. If you are using the high losses substrate, you can suppress the surface rate, right? So what are the way to reduce the surface rate? Like electromagnetic band gap structure, metamaterial structure, another structure you can utilize, and you can improve the gain, right? So ultimately, to improve the gain is basically to low lossy material, or you can reduce the surface.
Okay, sir. Sir, what are the requirements for creating a slot and feeding elements in the antenna structure?
What are the requirement for?
Requirements for creating a slot and feeding element in the antenna structure.
For creating the slot, it's completely up to you. What are the your application? I mean, let's say creating a slot is one way to miniaturize the antenna structure electrically, right? So let's say your whatever resonance frequency you want to target, your without changing the footprint of the antenna structure, you can select the shape and size of the slot. You can optimize the shape and size of the slot corresponding to the frequency wavelength. Then you can place and you gain the performance. But making the slot randomly is very tough, because sometimes you have to formulate. And what is the formulation is there for the slot? You can just go through the slot antenna design criteria, and you will get lots of technique of the slot design, right? You can create the slot, you can create the sleeve, and what is the difference between slot and slit? What is the effect? You can see that. And there are no any fixed criteria for placing the slot, right? I mean, you can just tune. Ultimately, what is the position of feeding point? Well, feeding point should be where the maximum impedance is matched between the transmission line and antenna, right? Let's say we have the 50 ohm transmission line. Our antenna position should be our antenna feed point should be 50 point between the maximum and minimum. You can search and you can place, so the maximum power can be transferred. Similarly, the slot position in such a way that where current is going to be maximum, you place the slot at that position, then maximum alteration of current will happen. So that will create the larger impact over the antenna design, antenna performance, rather than random placing of the antenna structure. So this is the one major criteria to placing the antenna slot structure, creating the slot structure for the antenna.
Yes, sir. Sir, next question is, if we are using DGS structure, then bandwidth increases. What is the mechanism behind it and that it increases the
Can you
bandwidth?
repeat? If we are using the DGS structure, then bandwidth is increased. What is the mechanism? So actually,
Yes.
DGS placement is over the ground plane. Now, right? How it can how can we justify means its mechanism is what defective ground structure is actually placed over the ground, and the different mechanism of this ground structure is there. Maybe in sometimes we protrude the ground plane, maybe we create the alteration in the ground plane in the asymmetrical manner, right? So basically what is happening when create the asymmetrical manner alteration, certain L and C like capacitance and inductance we introduce in the structure. So to improve the bandwidth, what we require, we nullify the inductance effect over the antenna structure, improve the capacitance and quality factor, right? So if you are creating the structure in such a way that which do this thing, then ultimately it not only contributes to the bandwidth enhancement, but also it will increase the overall isolation between the antenna structure. Okay, so that's why TGS can be utilized in both way. Like sometimes utilize for the isolation enhancement, but you can see sometimes that the same can enhance your bandwidth also of the antenna performance. So how it is coming? It is coming from the LC geometry also itself, right? So it's a mechanism is coming from the picture of LNC creation and quality factor improvement also.
Yes, sir. Sir, how to design ECM for any antenna? Can you show that with an example if you have any
ECM,
slides for
ECM is
uh, sir, equivalent circuit model?
okay. Equivalent circuit model I don't have any with me, and but equivalent circuit model you can design with the transmission line theory, because simple microstrip patch antenna or simple circular patch antenna, rectangular patch antenna ECM is very simple. You can simply formulate the RLC and you can connect and take the formulation. But in the mobile case or any complex geometry, formulation of like this ECM is not very easy, because lots of mutual coupling, lots of inductance, capacitance play very important role. If any very complex structure is going to formulate with the equivalent circuit modeling, is not very easy. Some of the simple microstrip patch antenna we can formulate. That's why you can see in most of the mobile cases there are no any electrical modeling are there. Only simulation, experimental validation is there, right? So always it's not true to do the modeling with the complex structure. That's why in the literature also you cannot see the very complex structure have the electrical circuit modeling.
Okay,
I
sir.
don't have any slide of this equivalent circuit modeling in this lecture, but later on I can search and provide.
Okay, sir. Sir, that diversity gain that you have explained, sir. Sir, for that only the participant is again asking that means how the number of elements, like for 4 or 2 elements it is 10, for 4 elements, how it approaches, sir. Communication people give this approach.
Diversity gain changes with the number of elements. Yes, it changes because the combined signal to noise ratio of the antenna system is maximum. Let's say maximum combining ratio you are utilizing in the biodiversity technique. So maximum combining ratio will what they do. They take the signal to noise ratio from each branch, and they combine, and how much improvement of signal to noise ratio with respect to single antenna system is there, that will give the your diversity gain. So as we increase the number of antenna system, yes.
Yes, sir. You can continue, sir.
So that's why if we increase the number of antenna system, ultimately our overall performance, you see channel capacity I show you, as we increase the number of antenna, our channel capacity, data rate increase. So in the similar way, but it maximum in the ideal scenario you can get the thing.
Dear participants, if you have any more questions, you can please put in the chat box. Sir, I think now there are no more questions.
Okay, ma'am. Thank
So
you.
thank you so much, sir. On behalf of EICT Academy and MNIT Jaipur, thank you so much for accepting our invitation and enlighten our participants, sir.
Thank you,
It
ma'am.
was very wonderful session.
Thank you.
Thank you, sir. Dear participants, next session will be from 4 p.m. in the evening. You are requested to kindly join by 3:45.
Can I log off?
Yes, sir.
Okay, thank you.
Thank you, sir.